Hey everybody, it's Ripley back again. We're going to talk about rates of change in the sciences. This is a pretty easy section, but there is one example that shows up in every textbook that you've ever seen, all right? So I want to make sure that I cover it because it's important and it really hits pretty hard in terms of this is kind of our first application of derivatives. But the first thing that I want to cover is rates of change in science in general. And really, the only thing that's important out of this section, other than the example that I'm going to do, is the fact that what we need to be able to do is start looking at a Leibniz notation for a derivative and asking ourselves, okay, what is the independent variable and what is the dependent variable? So let's say, for example, that I have this dq over dt. So I have a rate of change of something. Well, this automatically tells me, if you recall, if I look at it in my standard form, I've got y as a function of x, or f of x, or just y, right? You with me? So when I look at this guy, I need to be able to see that my mother function, the function from whence the derivative came, is q of t. The t is the independent variable. The denominator, the d, this little differential, which is what we'll talk about here in a little bit, this little differential of x, that in this case is the independent variable. Likewise, this little t down here is the independent variable. The dependent variable is a q, and anything else is a constant. So I can throw the most god-awful, ugly-looking thing you've ever seen. Like if I do q of t is equal to 4 eta sigma squared divided by root 2 pi r times t squared. Hey, guess what? All this garbage is just a constant. So when I'm looking for dq over dt, hey, guess what? This constant just slides down, and ooh, Ripley, this is so hard. What's the derivative of t squared? Well, 2t. Right? That's all that it is. So this guy would be in here, you'd have this 2t, and you're done. So you end up with like applications in chemistry and physics and biology, wherein you're going to have just these god-awful formulas, you're going to be afraid of them. But if you look at the derivative, or if you look at the function and determine what's the independent variable and what's the dependent variable, and if it ain't one or the other, then it's a constant. It's along for the ride. It never varies. You have to have a value to plug in for that. Or you just leave it as a constant flying along like I did with this awful 4 eta sigma squared over root 2 pi r. That just floats right on down in here. 4 eta sigma squared over root 2 pi r, right? Times 2t, and I'm done. That's it. That's really it. It's literally that simple. Now, clearly, you're going to have problems where you have to be far more analytical and far more thoughtful. But at the end of the day, if you let the derivative notation sort of grab you by the nose and walk you through, or if you let the function notation, like as in here, I've got q of t. So I know q is the dependent variable. I know t is the independent. So my eye just starts looking for t's. Not a t, 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 not a t. Doot, doot, and I'm done. That's the thing I take the derivative of. Everything else is along for the ride as a constant. Okay, enough said. What I'm going to do now is I'm going to do a world-famous physics problem that shows up, like I said, in almost every textbook ever, okay? So what I'm going to do is I'm going to let x of t be the position of a particle. And then I'm just going to answer a bunch of questions about it. I'm going to do t cubed minus 6t squared plus 9t. So this is a particle. Its position is, you hand me a time and I can tell you where it lives on the x-axis. So if you have me time t equals 0, I know that x of 0 is equal to 0, right? Because 0 cubed minus 6 times 0 cubed plus 9 times 0, blah, blah, blah. So this thing, when I start looking at it, is sitting at the origin, right? It's sitting at x equals 0, right there. Now, but there's some questions that we have to ask. Is it moving left? Is it moving right? Has it stopped? Is it at a standstill? You with me? Is it speeding up? Is it slowing down? If it's moving left or right, how fast is it going? If it's accelerating, if it's not accelerating, if it's accelerating in a positive direction or a negative direction, and if so, how much? And those are all questions that we're going to ask. So I have an old example from an old textbook, and I'm going to walk you through it. The first question for this problem is, what is the velocity at time t? So what is the velocity? Well, if this is position, we know this from when we first started putzing around with derivatives, right? We know that the derivative of position is velocity. So I know that v of t is equal to x primed of t, which is equal to 3t squared minus 12t plus 9. Now, little technical advice here. Notice I did a bad job on that one. Notice that my t's are hooked. I will also do that with my i's. I'll kind of hook them at the top. The reason I do that, and it's a perfect example right here, is if I don't do that, then I may screw up my t's and my pluses, which could cause me to make an error, not of knowledge, but of technique. So be careful. Likewise with i's can look like ones. Okay? So part B in this problem says, what is the velocity at t equals 2 and t equals 4? Well, if I want the velocity at t equals 2, don't I just stick a 2 into here, which is just 3 times 2 squared minus 12 times 2 plus 9, right? Nothing to it. This is 2 squared is 4, right? 4 times 3 is 12. 12 minus 24, because 12 times 2 is 24. Negative 12 plus 3 is negative 3. So what does that mean? What does that mean? If the velocity is negative, then what is the particle doing? It's moving left. If the velocity, so over here at t equals 2, the particle's moving in the left-hand direction because velocity is negative. Okay? V of 4, same thing. It's going to be 3 times 4 squared minus 12 times 4 plus 9, right? Let's see if I can do this relatively quickly. 3/16 is 48 minus 48 plus 9. Hey, that's pretty easy. That means out here at t equals 4, the particle is moving to the right. Easy, isn't it? Okay, how about C? Let's look at this guy. And in mine it says, when is the particle at rest? Well, what? When the particle? Particle at rest. How am I going to figure that? Oh, wait. A particle is at rest when the velocity is equal to 0. Hey, wait, I got velocity right here. So all I have to do is go, all right, 3t squared minus 12t plus 9 equals 0. And then let's do some algebra. What the heck? This is 3 times t squared minus 4t plus 3. Oh, that's a trinomial. That's easy enough to factor. This is equal to 3 times t minus 3 times t minus 1, right? Double check it if you need to, which implies t equals 1 and 3 is what is v of t equals 0. Done. Algebra makes total sense, doesn't it? All right. How about let's do D. D said, when is the particle moving forward and when is it moving backwards? Well, this is actually pretty simple to do. Let me show you. Because we just said that the particle is moving forward when the velocity is positive and it's moving backwards when the velocity is negative. So let's use our good friend called the sign chart. Now, I will megalomaniacally refer to this as the Ripley-Doodle diagram down the road. However, for the time being, let's just call it a boring old sign chart. All right, so here we go. I know that the particle stops at t equals 1. I also know that the particle stops when t equals 3. Now, it could be argued that we don't care about any values when t is equal to 0. So let's hook this guy over here at 0 and say, okay, we're only playing ball from t equals 0 out to infinity. All right? Now, I'm going to test values. Hopefully you learned this in Algebra 2, but if you didn't, that's no problem. We can fix it. I don't care about values. I don't care about actual numbers in the spaces between these zeros. What I care about is sign. I care if it's positive. I care if it's negative. So if I pick a value between 0 and 1, call it 1/2, let's see what happens. 3 is always positive. If I put 1/2 in here, 1/2 minus 3 is negative. So I'm going to get a negative here. If I put 1/2 in here, 1/2 minus 1 is also negative. So what I have is a positive times a negative, which makes that positive. Let's pick another value. Let's say 2, because 2 lives between 1 and 3. I could pick any number between 1 and 3. But Ripley, how do you know it doesn't change? Well, if it were to change signs, I would end up with another 0, wouldn't I? So I'll just grab 2 because I'm simple country folk and that's easy. If I put 2 in, that's always positive, that's negative, and this guy is going to be positive, right? 2 minus 1 is positive. So a positive times a positive is negative. Now let's put a number to the right of 3. How about 10,000? Or you can put 4 or 5 or any other number. We know that the thing's not going to change signs, otherwise I'd end up with another 0. Remember that whole intermediate value theorem thingy-dingy? So let's put 4 in there. 3 is always positive. 4 minus 3 is positive 1. 4 minus 1 is positive 3, so I get a positive times positive. Hey, look at that. Which means that what this thing does, what this curve does, is at t equals 0, it's moving to the right. When I look at it, think of it as though it's a cheetah. Well, not a cheetah. That would be a really quick turning cheetah. Well, I reckon it could be. It doesn't really matter. At t equals 1, it's moving to the right. And then, or excuse me, t equals 0. And then at t equals 1, it stops. And it starts moving after that to the left. And then at t equals 3, it stops again. And then it continues to move to the right forever. All right, that's what the particle's doing. Like a bead on a wire is really what it's doing. You can think of it like a spider moving back and forth on a horizontal wire. All right, that was easy enough to figure out, right? We use all of our fun algebra from back in the day. All right, I'm going to move over here because I want all my space. I want this, if I can do it, I want it to fit on one page so you can look at it all at once. All right, this is probably one of the more important ones that we have to deal with. Let's do E. I want to know, let's say the total distance traveled. I'm going to write this one down because this is important. Total distance traveled in first 5 seconds or 5 time units. Okay? First 5 seconds. Now there's a problem, and students just love to get really crazy with this. They will say that the distance is equal to x of 5, the position after 5 seconds, minus the position when it started. Now you may think to yourself, wait, something feels fishy about this because this thing's moving around. Okay, well, let's think about this. The distance that it's, or the position when it started minus the position when it, this would be the position when it started, subtracted from the position when it finishes, that wouldn't be distance, would it? Because what's happened is this thing would go, it goes here, and then it comes back, and then it comes back. And let's say that this right here was t equals 5. Well, if I took the distance from here to here, that would be about, what, 1, 2, 3, 4 units. But the thing has gone this many units this way, this many units this way, and this many units this way. So it's moved to the right, then the left, and then the right. And x of 5 minus x of 0 does not take any of that swerving back and forth into account. None, 0. So this is not distance. What it is displacement. And what displacement is where the particle stops with respect to where it started. If I want the distance, well, how do you think I would do that? It's pretty easy. With the distance, all that I do is I take every place at which it stopped. I have to take that into account. So do you agree that I could take x of 1 minus x of 0, and that would give me the displacement from 0 to 1. Now I got to be careful, because displacement can be negative and distance cannot. So the way around that is we slap absolute values on there. Displacement is allowed to be negative. If I end up left of where I started, displacement would be negative. So I slap absolute values around it. Then I would add to that from t equals 1 to t equals 3. So I would just go, all right, this is going to be x of 3 minus x of 1. And you're probably going, Ripley, does it matter? No, because I put absolute values around it. It can be negative. Who cares? We're gonna force it to be positive with absolute values. To that, I'm going to add x of 5 minus x of 3. And very much like a cooking show, excuse me, what comes out, and you can verify this, is 28. It goes 28 units. This would be the distance. Now, if you look close, x of 0 we knew was 0, right? So x of 5, if I want the displacement, x of 5 minus x of 0, I know that x of 0 is 0. So this would simply be 5 cubed minus 6 times 5 squared plus 9 times 5. That's a 5. And then minus 0, right? And this guy would be 125. 6 times 25 is 150. So minus 150. Plus 9 times 5, which is 45, right? And what would I get? Let's see, negative 25 plus 45 is 20. those are different. 20, last I checked, is not 28. Let's make sure that I did that right. 6, 25, 95, I got that, I'm good. Yeah, I like it. So what happened was, between here and here, what we lost was, we lost 8 units that were carved out by this back and forth motion. And that's a really, really common problem that shows up often. All right, let me scooch over here. Let's do F. And let's see, F for me is, how about, let's say, what if I want to find the acceleration of the particle at time t? Find acceleration at t. Well, how do I get from velocity to acceleration? We talked about this. Take the derivative. I know that a of t, acceleration of the particle, is equal to x, is equal to, well, screw it, is equal to x double primed of t, which is equal to v primed of t. Which in this case, let's see, v of t is what, 3t squared minus 12t plus 9. So the derivative of velocity is going to be 6t minus 12. Now, you may already have a hankering for what we're going to do with this, but let's play with this a little bit. So if I wanted to say find the acceleration at, I don't know, at t equals 4. Well, that's easy, right? Just plug it in. I got 6 times 4 minus 12. 24 minus 12, last I checked, is 12. So it's accelerating to the right. It's accelerating to the right at 12 units per second. We also know that it's moving to the right. So this thing is definitely speeding up. True? It's kind of an interesting way of thinking about it. So if I wanted to figure out if it were speeding up or slowing down, hey, let's do that next. Let's do that next. If I want it, let's do E, F, let's G. The very last problem is, when is the particle speeding up and when is it moving down? Well, watch how cool this is. What I'm going to do is I'm going to drop right under here. Oh, God, that is a bad line. I'm going to put A of t down here. I'm going to put 0 here. And hopefully you can see that if I set acceleration equal to 0, then I get t equals 2. So I know there is no acceleration at t equals 2, which we will put right in between 1 and 3. All right? Now, students will often, they'll get really screwy. Excuse me. They'll get really screwy with the idea of speeding up because they think that it's speeding up when the velocity is positive and it's slowing down when the velocity is negative. But if you think about that, that can't be true, can it? Because if I've got a negative acceleration on a particle whose velocity is positive, I'm slowing it down. If I have a positive velocity on an acceleration or on a velocity that's moving left, I'm slowing it down. So what does that mean? Well, let's fill this chart out first. If I plug 1 into the acceleration, whoop, it tells me right there what to plug it into. I get 6t, I get 6 times 1 minus 12, that's going to be negative. If I put 15,000 in, 6 times 15,000 is a really big number, minus 12, and I'm going to get positive. So I know that any time that my velocity and my acceleration are the same sign, then I'm going to be speeding up. Anytime that they are opposite signs, I'm going to be slowing down. So watch. I know that I'm speeding up. Well, let's check. If I drop this, here's 1, and here's 3. This is 3. I know velocity is positive from 0 to 1. Acceleration is negative from 0 to 1. So I am slowing. I'm slowing, let's see, from 0 to 1. Now, what do I do? Is this parentheses or not? Well, is it? What is it going to be? It's got to be parentheses because velocity is 0. It has no sign. So there's no such thing as having air quotes the same sign. I also, let's look at another one. How about from 1 to 2? Well, now the velocity from 1 to 3 is negative. The acceleration from 1 to 2 is negative. So I know that I'm speeding up from 1 to 2. Again, there's no acceleration at 2, so I don't include 2. Let's look at from 2 to 3. Velocity is negative from 2 to 3. Acceleration is positive from 2 to 3. They are opposite. So the way I do this is with a union sign, and I go from 2 to 3. That's when I'm slowing. They're opposite signs. All right? And then last but not least, velocity is positive to the right of 3. Acceleration is positive to the right of 3, so I am speeding from 3 to infinity, which is crazy because eventually you're going to break light speed, theoretically. Right? All right. Now, let's look at this is an interesting algebraic approach to answering this question. Let's answer it graphically. Let's say, just for giggles, I'm just making this up out of my ear. Let's say that my velocity looked like this. And we're going to go from 1 to, let's say, whatever this is. Let's call that 10. And this is v of t. And I want to be able to look at the velocity because we know what our graphical emphasis is in this. I want to know when is the function, when is the particle x of t. So x of t, we don't know what it is. We can't see it. We could sketch it if we had to, right? We could put a 0 and a 0 and this thing's negative. But yeah, we're not going to get into that right now. That's all stuff that we've done before and that we'll do a great deal more of before the end of differential calculus. But let's just think for a second. This guy right here is v of t, and I want to know when x of t is speeding up. Well, remember what we just said. If x of t is speeding up, then velocity and acceleration are the same sign. So if velocity is increasing, right? If it's positive and increasing, then velocity is positive, and its acceleration, which is the first derivative, remember, a of t equals v primed of t. Now this is where we get to wrap all these derivatives into one tight little ball. So I know that from, let's call this my top, man, my drawings have been horrible. I know that from 1 to this value here, let's just call it a. I know that velocity is positive and increasing, which means it is speeding up from 1 to a. It's speeding up in the right direction. Now, from, let's call this guy right here B, and then I'm going to call this guy right here C. I know from A to B, velocity is still, this is going to be speeding. This is speed. From A to B, velocity is still positive, but it's decreasing. So the slopes of lines tangent are going to be negative, which implies that the acceleration is going to be negative. So velocity is positive, but acceleration is negative. Therefore, from A to B, it's slowing. How about from B to C? Well, velocity is negative, it's below the x-axis, and it's also decreasing, which means its acceleration is negative, which means it's speeding. It's speeding up in the left direction, right? From C to 10, we're going to ignore everything to the right of 10. From C to 10, velocity is negative, it's below the x-axis, but its tangent lines, or its acceleration, is going to be positive because it's increasing. So velocity is negative, acceleration is positive, therefore it is slowing. And guess what? We have a graphical analysis of this phenomenon. All right, you're going to do a bunch of these. They're fun, they're cool, it's an interesting way. You'll see them in your physics courses. That's really what we're doing this for. I want to make sure that you see it in your physics, or I want to make sure that you see it before your physics courses or while you're taking your physics courses to give you a little more depth of understanding about what's going on. All right, thank you for your time and attention. I hope you enjoyed the lesson, and I'll see you in the next section.